Hello! In this video, we'll explore both GPU and CPU usage in PyTorch. We'll build a model and show you how easy it is to leverage GPUs for significant performance gain. We're starting in a Colab notebook, focusing first on the CPU side. We'll connect to the standard Colab runtime for our initial CPU testing, and later switch to a runtime with a hardware accelerator like an NVIDIA GPU to see the difference. Let's dive right in and build our model. We'll create an image classification model using an American Sign Language dataset. First, we'll perform some imports. From these imports, you can see we'll be using the Atom Optimizer from PyTorch, various data utilities, and pandas to explore the dataset. Even though we know we don't have a GPU available yet, we can verify the setup using the torch CUDA is available method. Next, let's proceed with using the Kaggle dataset. This is the Sign Language MNIST dataset containing about 27,000 examples of American Sign Language images. We have both training and test data with labels from 0 to 25 corresponding to the 26 letters in the English alphabet. We could download this dataset directly as a zip file, but let's write code to handle this within our notebook. We'll import Kaggle and use the dataset download method, making sure we have the correct dataset ID. The output path will show us where our dataset is stored. It appears in the cache directory, which works perfectly for our needs. Now let's load our training data frame using pandas, specifying the path to the training CSV file. We'll do the same for the validation data frame as well. Great, we've successfully imported the data we need. Let's extract the labels for our supervised training task from those pandas data frames by grabbing the label column. We'll do this for both data frames, giving us separate variables for our labeled results. We'll also extract the image data, assigning it to variables for easy access. To give you a sense of the data size, each image is represented as a flat array of 784 pixels since they're 28 by 28 pixel images. The labels correspond to individual letters of the English alphabet. Before we proceed, it's a good idea to do a quick visualization check. Let's grab our very first data point to see what we're working with. All right, here's one of our images. At 28 pixels by 28 pixels, these are not particularly high-resolution images. We can also see the actual label. For example, this is the 17th letter in the alphabet, and it's the 17th because we're 0 indexed here. Remember, in programming, we often start computing from 0, so even though it says 16, we're actually detailing the 17th letter of the alphabet. Next, we need to do a normalization exercise. Let's look at the training minimum and maximum. Our max is 255 and our minimum is 0. Usually we want to normalize these values to be between 0 and 1. This will make training more efficient and help our neural network converge more smoothly. So let's do that normalization for both our training and validation data frames. We've already extracted these values, so let's use them directly for our X training and X validation. Now let's create our own dataset using the PyTorch dataset class. We're going to create a subclass called Sign Dataset for Sign Language, which will inherit from the dataset class that we imported. We need a few essential methods here. We need an initialization method, init, where we'll ensure the data is converted to floats. We need both the x and y, basically the images and the labels. We'll also define the getItem method to retrieve individual samples, and finally the len attribute to return the size of the dataset. This is looking good now. We can pass this to the data loader for model training. Let's define a new training data variable, which will be our sign dataset, where we pass our pre-processed images and labels. The data loader class within PyTorch will be helpful for us here. For improved training performance, we can also specify a batch size. For verification, we can print out the length of our dataset, which gives us the number of images that we expect. That looks good. Let's do our validation work as well using the exact same custom dataset class. Consistency is key here. In the validation dataset, we have about 7,000 image label combinations. This should provide a solid evaluation of our model's performance. Now, let's move on to actually building this model. We have an input size of 28 pixels by 28 pixels and a number of classes equal to 26. It's time to bring it all together and build out our neural network. As usual, we use the neural network library that we imported from PyTorch and give ourselves a few layers in this network. First, we'll flatten the images, then add linear layers and ReLU activation layers. So we basically want an input layer, a hidden layer, and then an output layer. This architecture represents a simple multi-layer perceptron with one hidden layer, a good starting point for our problem. With that model specification looking good, let's go ahead and time a compilation here. We get about 10 seconds or so for that compilation. We define a cross-entropy loss for our loss function, and we'll use the atom optimizer for our optimization function. The atom optimizer is efficient and works well across a variety of problems. Now comes the exciting part, the training loop. And we're going to be using those data loaders that we created earlier. We'll define this training loop in a single train function, and of course, we'll keep track of both loss and accuracy as we go. To get this training function to work, we'll want our batch accuracy calculator. Once we've defined the training loop and the batch accuracy calculator, we're ready to run our training over a few epochs. And of course, we'll want to time the function here. . While time is running, we notice from the syntax highlighting that we probably forgot to define our validation function. Let's be proactive and go ahead and do that. To track our progress, let's print out the loss and accuracy as we go for both the training and validation. We'll do that at each epoch. Monitoring the loss and accuracy at each step will help us understand how well our model is learning. All right, so we get a little bit of an error here as expected. Encountering errors is part of the process. Now that we've defined our validation function, let's run it again and see how it goes. As that training run completes, we see that it took about 1 minute and 30 seconds. Now we have our model and the trend here looks good on both the loss and accuracy. We have a loss that's dropping and an accuracy that's improving. Now, as a quick bonus here, let's look at what happens if we change the runtime. Let's go for an NVIDIA GPU. This gives us an idea of how much faster or potentially slower this is going to run when we have a GPU. So now when we run CUDA is available, we get true. We could proceed through a lot of these cells as we did before, but we're going to need to make just a couple tweaks as we go so that we can actually push the model to our GPU and make sure that it's properly utilized. A lot of the pre-processing stuff is going to be the same. But when we get to our dataset definition here, one thing we're going to want to do is push this to our CUDA GPU device. We'll do that for both the images and the labels. An additional piece we'll want to do is basically push our model itself to the device. We'll compare the times here, so we had about 10 seconds of wall time when we did this on the CPU. Let's see what happens when we do this initial push to the GPU. We have a little bit of a faster time here compiling the model when it's on the GPU. Let's keep going here. We have the same training and validation functions, and again, we had 1.5 minutes of wall time for our training run when we did this on the CPU. Let's see what we're looking at with the GPU. So we get a significantly faster training time with about 21 seconds of wall time when we're using the GPU. That's a huge improvement, reducing our training time from 90 seconds down to just 21 seconds. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. If you have any questions, please post them in the comments section, and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.